welcome to our blockchain seminar. So I'm really very pleased to welcome you to our seminar. And Akira Takahashi is a PhD candidate at Aarhus University in Denmark. And today he is going to talk on his latest paper on lattice-based multi-signature scheme. Thank you again, Akira. Now the screen is yours.
Yeah, thank you very much for having me. So let me share the screen. Is it visible?
Yes.
Okay, good. Yes, yeah, so thank you very much. And also nice to meet you, everyone. So my name is Akira. As introduced, I'm a PhD student at Aarhus University. So this talk is based on a joint work with Ivan Damgaard and Claudio Randi from Aarhus University, also Mehdi Tibsh from Entity Corporation in Japan. And ePrint is already available here. So if you're interested, you can have a look at more details. So as it's the first time, let me briefly introduce myself. So right now I'm a second year PhD student, and my supervisors are Claudio Randi, who is also co-author of this paper. Also Diego Aranya is my co-supervisor. And prior to joining Aarhus University, I was an intern at the Entity Corporation in Japan under the supervision of Mehdi Tibsh, who is a co-supervisor, co-author of this paper. So actually, this is how the collaboration between Aarhus and the Entity happened. So I've been working on a few different topics. The first one is side channel attacks against the signatures. Also, I'm interested in provable countermeasures. So this has been my main focus. And recently, I'm also interested in construction of multi-party protocols. So this manuscript is actually my very first work on MPC. Also, my very first work on Lattice as well. Okay, so this paper is about our new lattice-based and auto-ebb signatures and multi-signatures that have a low round complexity. And we provide full security proofs in the random oracle model. So particularly, our construction is derived from the Fiat-Shamir with abort paradigm, which I'm going to explain a bit later. And the main technique of this work is the application of a homomorphic commitment. So why is it good? So actually, there have been a few different similar construction following Fiat-Shamir with abort paradigm. However, we found that the security proof of those schemes are actually incomplete. So by applying this homomorphic commitment, we can actually show that the security proof can be completed. So here I remarked that we are not claiming that the previous constructions are insecure. It's just that the certain crucial step is not explained. So it may be that you could patch in a different way. And actually, the use of homomorphic commitment is not just for completing the proof. So actually, by instantiating the commitment with a trapdoor commitment, we can achieve the two-round protocol from Fiat-Shamir with abort, which is, to the best of our knowledge, never proposed before. And then in this talk, for the sake of simplicity, I'm going to focus on two out-of-band signing protocol, assuming that the key shares are already distributed. And but essentially, the observation I give here can be naturally generalized for an out-of-band signing with a dedicated key generation protocol and the multi-signature in the plain public key model. So,
Akira?
Yes?
Can we ask questions during the presentation?
Sure.
When you say homomorphic commitment, do you mean like fully homomorphic commitment, or is it enough if you have just additive homomorphism?
Good question. Yeah, so in this construction, actually, only additive homomorphism is needed. So of course, we can instantiate the protocol with FHE, but normal additive homomorphic commitment is sufficient for this.
Okay, yeah.
Yeah, so, yeah, by the way, so since I think I have a sufficient time, so if you have any questions, please feel free to interrupt me. Okay, so I'm going to briefly introduce the topics two out-of-band signing and fiat-Shamir support. So the background of this work is as follows. So as you probably know already, there's a NIST post-quantum crypto standardization process. And recently, round 3 candidates have been announced. And two of them are lattice-based signatures. And those signatures follow two different major paradigms. The first one is called hash and sign, which essentially follows the GPV framework. And Falcon is a concrete instantiation. And the second one, which I'm going to talk about in this work, is fiat-Shamir with boards. And the Delirium is actual instantiation. So if you look at fiat-Shamir with a board style signature, it actually has a structure very similar to the discrete log based counterparts. So, and then looking at the existing works, there have been different round efficient and party Schnorr style signatures. So this is actually unlike the ECDSA, threshold ECDSA, which is recently very actively studied. So unlike ECDSA, distributed Schnorr signing is actually more straightforward. And you can make the 2-round or 3-round protocol from Schnorr. So here we got a question. So can we, using the observation from discrete log setting, can we construct a lattice-based and a round efficient multi-party signing protocol? So in this work, we answered this question in the positive, but there are some subtleties. Okay, so what is a two out-of-band signing? So here, Alice and Bob are signer. And then there's a single secret signing key, which is not known to either of Alice or Bob. And first, this single signing key is split into 2 parts, and Alice and Bob hold a share of a secret signing key. And then they both agree on some message to be signed. And after some interaction, they output some signature. And of course, the correctness property should guarantee that as long as Alice and Bob honestly follow the protocol, then the output signature should be verified with a public key, which corresponds to the secret signing key. And also, the game-based security notion can be defined as well. And this is analogous to the normal unforgeability against chosen message attack game. So here we assume that one of the parties is corrupt, and then this adversely has one share of the signing key. And then adversely is able to query honest party, Alice, with some message. And then the adversary is able to generate some signature corresponding to query the message. Then after some interaction or sign queries, adversary outputs a forgery. And then the unforgeability requirement is that basically the probability that the forgery is verified with a corresponding public key can be verified is negligible. Also, the forgery includes a message that is different from any other message that has been queried. So that's the game-based security notion. And also here I assume that key shares are already distributed in advance by some trusted party. But in practice, key generation part is also done in an interactive fashion. So in this case, first corrupt party and Alice execute the key generation protocol, and then after this, sign queries are out, and then the public key is also the one generated in the key generation protocol. So that's the security that we want to consider. Okay, so now Fiat Shamia with the boards. So I assume that I think most of people here are familiar. So I'm going to quickly go over this. So Fiat Shamia with the board paradigm basically follows the standard 3-round Sigma protocol. So here I present the division identification protocol, which operate on the vector of polynomials in this quotient ring. And the polynomial f is usually a power of 2 cyclotomic polynomial. And then here, the secret key is some small ring element. And then public key is some random matrix concatenated with some identity matrix. So this means that we actually work on a hidden number, the Elmington normal form. Then, so in the first phase of the Sigma protocol, first prover samples randomness from some distribution, which is either Gaussian or uniform distribution over some small range. And then send the commitment A times Y. And then the verifier returns some challenge. And then construct the response value. And here, the special care is needed. So this response value is actually not uniform because S is small, and accordingly Z has to be small. And also this Y is small, so the constructed Z is actually this depends on secret. So here the so-called rejection sampling is needed. So after this rejection sampling, the prover can make sure that the response value is independent of the secret values. Then finally, the verifier checks the correctness, and also verifier also needs to check that Z is actually small. So this, except for this rejection sampling part, all the operations are actually linear. So we can actually see some correspondence between Fiat-Shamir with a board type signature or identification and Schnorr type identification. So here, in the case of Schnorr, everything is linear because we don't need any rejection sampling. So using this observation, we can actually reuse some observation from Schnorr type protocol to construct a distributed identification for, distributed signing for Fiat-Shamir support. So a bit about security. So soundness, this can be proved from module SIS and module LWE. So here, if we assume that some cheating prover can correctly answer 2 different challenges. So first, we assume that due to the LWE, the public key T is indistinguishable from a uniformly random value. And then, thanks to this equation, if the prover can answer 2 different challenges using these 2 transcript, you can actually construct a solution to SIS problem for the instance matrix A concatenated with T. So here again, T is uniformly random. So this can be actually regarded as an instance of the SIS. So that's the idea of division identification. Also, zero knowledge can be proven. But here we have to be a bit careful because actually the zero knowledge is only proven for non-aborting cases. So for non-aborting cases, you can actually do the standard simulation. However, if the protocol aborts, at least in the literature, there is no known way to simulate the rejected transcript. So this is going to be a subtle issue when we construct the distributed signing. So I'm moving to two-party signing. Is there any questions so far?
I can ask a question about this simulation of the aborts.
Sure.
So here I mean, there is already a technique that you can use, like you commit to your first move first before sending this, what was it called? W, I think?
Yeah, so now we are using W, yes. Right. So yeah, that's a good point. So that's exactly the technique we're going to use when we construct the distributed signing.
Yeah, but
So
this is already known.
Yeah, I know. Yeah, so of course, yeah. So you're saying that first, the prover, instead of sending W, sending a hash of W or commitment to W, and then yeah, that's correct. Yes, of course. But so that technique. Okay, so I'm going to explain this two-party signing.
Okay.
Yeah. So that's actually a very critical point. So okay. So when we consider two-party version, we can construct a very straightforward protocol. So let's call it a bare-bone protocol. So thanks to the linearity, most of the operations can be done locally. So here, again, the prover 1 or party 1 generates Y and W independently, and then two parties exchange W1 and W2, and then they add them up. And then, so of course, thanks to the linearity, this W1 plus W2 contains a matrix times Y1 plus Y2. So now, and each party does a rejection sampling locally, and then if both parties pass the rejection sampling, they can exchange Z1 and Z2. But actually, this bare-bone protocol is not secure. So there are two issues. So as I mentioned, so we don't know how to simulate this W if Z gets rejected. And this is usually not a problem for single signer setting or non-interactive zero knowledge, because in this case, there's no reason for prover to reveal rejected transcripts. And this becomes problematic in interactive setting. However, so as you mentioned, so you can, of course, send a commitment commitment to the first W, and only reviews the W when rejection sampling passes. However, in the previous similar Fiat Shamir with aborts based multi-signatures, they didn't use any commitment or anything. So they just sent W in the clear in the first phase, and whether the party aborts or not, this W is known. So this is why we want to add a commitment, and especially it's important to have a homomorphic commitment, because here we are relying on the homomorphism of W1 and W2. So of course, if you simply send the hash of W1 or W2, then you can't add them up. So instead, we really need a homomorphic property here. So I hope this answers your question. And then the second problem is that the malicious party could actually choose the first message W2 depending on the first message W1. And so this is why we need some extra round. So we actually first need to commit to the first message W and then open later. And this is important for the simulation. And actually, without this committing phase, we can actually describe a sub-exponential attack. And again, this is variant of the sub-exponential attack against the discrete log-based multi-signature. So here I'm going to sketch this attack. So against this bare-bone protocol, we assume that the malicious party has a share of S, and then the public key is again the sum of the AS prime plus AS. So here first adversary starts K concurrent sessions on the same message, and then receive W values from the honest party. So here adversary holds in the protocol. So first adversary add those W values up, and then adversary is to find some message and the response value W, such that the hash of these values satisfies this equation. So this means that the output of the hash of the added W's and some message is a sum of the hash of the W plus the adversary shares W. So actually this can be solved by reducing the problem to the so-called K-list sum problem. And in this case, we consider C as a vector. So we can basically solve this problem using a vectorial variant of the K-list sum problem. So then after solving this equation, adversely resume the sessions by sending back those adversaries share of W. And then the honest party returns its share response. So finally, adversely output some forgery. So here the forgery is sum of the response values sent from the honest party plus the joint challenge C star times adversary's share. So why does it work? So this actually passes the verification. So first, again, thanks to this K+1 list sum solver, this C star is actually a sum of each challenge value from each concurrent session. And then this forgery can be rewritten as follows. So now, because the C star corresponds to the sum of the C, the concurrent sessions, C from concurrent session, you can actually group them together. Then again, the sum of this Y value sent from honest prover, this corresponds to this W star, which adversary has found in the adversary used during this K+1 list sum solver. Okay, so then after this, you can actually check that AZ star minus C star T is equal to this W star. So this actually passes the verification. So of course, because now we are working on Fiat Xiaomi with reports, some care is needed. So of course, the verifier checks that Z star is small, so the number of the concurrent sessions should not be too large. So in this case, the parameter for the K+1 list sum needs to be chosen carefully. But anyway, so the point is that this is just for motivating why we need some additional step and why we have to avoid this bare-bone protocol. So okay, so now our solution. So again, so I already explained. So we apply homomorphic commitments to WI so that we can simulate the rejected transcript. And we actually hide this W until rejection sampling succeeds. And also, in order to prevent the concurrent attack, we actually use a commitment scheme that has trapdoor property. So this trapdoor property is actually crucial to avoid an extra round, which I'm going to explain a bit later. Okay, so now let's take a look at the secure 3-round protocol that uses the homomorphic commitment. So this is relatively straightforward. So here, those highlighted operations are differences from the 2-round part, to the barebone protocol. So in the first phase, we let the party to commit to the W, and also we have to actually exchange the commitment to this commitment. So this looks redundant. So I'm going to explain how to drop this procedure later. And then, first, the party 2 sends a hash of this commitment, and then the party 1 sends its commitment, and then receive the commitment, which is a pre-image of the hash commitment here. And then the party 1 checks that this hash of the commitment is actually correct. Then, thanks to the additive homomorphism, you can actually add the commitment up like this. And then do the rejection sampling. And if the rejection sampling was unsuccessful, then the party doesn't output anything. So this is why you can hide the first W, message W, which is a rejected transcript. So, right, so this is the 3-round protocol. So this actually passed the verification. So here, again, the verifier first derives a challenge and reconstruct the committed W, then checks that this W is actually a correct opening to the commitment. And the correctness holds because mostly because of the linearity of the order operation. So of course the SIS function is linear, so you can make sure that AZ minus CT is actually a sum of the locally submitted, the transcript, which is almost locally computed by both parties, but the challenge is shared. And the homomorphism of the commitment guarantees that the added commitment actually contains W1 plus W2. And we have to be a bit careful about the bound for the output signature. So especially if each share of Z follows the Gaussian centered at 0, then basically the norm of Z grows by a square root 2 when it's a 2-party. So what's the security? So this is provably secure thanks to the homomorphic commitment. So if protocol doesn't abort, we can just, the honest party or a core can be simulated with the non-abort honest verified zero knowledge simulator. And if protocol aborts, then thanks to the hiding commitment, it reveals nothing about the first message W. And in the paper, we gave a security reduction to LWE using the lossy identification technique. So in this technique, we can basically set the parameters such that for each first message of Sigma protocol W, there exists only a single challenge value that can be that leads to the accepting transcript. So this means, in other words, we are setting parameters such that SIS is vacuously hard. So existentially, with high probability, there's no solution for SIS problem. So this way we can avoid a forking lemma. So the security loss is smaller than the one given by forking lemma usually. And also for this instantiation, we use the commitment scheme that is computationally hiding and unconditionally binding. So, okay, so that's the security, and a bit more detail about the honest party oracle simulation. So now, I'm going to explain why this hash commitment is necessary. So of course, the simulator first generates the transcript Z, C, and W. So those are simulated transcript. And then thanks to the hash commitment from the adversary, by keeping track of the random oracle queries, actually the simulator can extract the adversary's share of the commitment 2, and then program the random oracle before sending back the first message of the simulator. So we want to, so this programming, this random oracle programming is very critical, COM1 plus COM2. And then also, so we simulator has to simulate the rejection sampling with some constant probability. It simply outputs nothing. Okay, so that's the high-level idea of the simulation strategy. So what about the efficiency? So for small number of parties, this construction is okay, but unfortunately, this doesn't scale very well. So the efficiency is a more open question. So there are essentially two issues. The signature size essentially grows by a factor of square root n, where n is a number of parties. So this is simply because of the fact that n discrete individual independent Gaussian samples, they sum up to another Gaussian sample, which follows Gaussian distribution with a larger standard deviation, and which is square root n times larger than the original standard deviation. However, the instantiation with Gaussian sampling, Gaussian distribution is still better than the one with uniform distribution. And also, since each party has to run rejection sampling locally, we actually need to wait for all n parties to pass the rejection sampling. So this means that if there are n parties, then essentially the expected number of restarts is m to the n, which is large. So in order to keep m to the n constant, again, the standard deviation has to be increased by a factor of n. Or alternatively, you can do many parallel repetitions so that one of the parallel repetition is hopefully passing the rejection sampling. Okay, so that was the 3-round protocol. So actually, so the main contribution with this work is to construct a 3-round protocol. So as I mentioned before, this first hash commitment seems redundant because essentially, basically what we are doing here is committing to the commitment. So this looks a bit strange. However, if you just drop this hash commitment entirely, the simulation doesn't work. So this looks more simple. So now both party submits commitments and they exchange commitments and then add them up and again exchange the response value. So if you try to simulate this protocol, there's an issue. So because there's no hash commitment coming from the adversary, basically there's no way for the simulator to know adversary's share of the commitment. So before sending back its commitment or its opening, there's no way for the simulator to program the random oracle with a challenge value chosen by the simulator. So this is an issue. So how do we circumvent this issue? Sorry. So also there's another issue. So actually, if the commitment key is fixed, then in fact, the same concurrent attack I described before applies. So this is why we actually need to be careful about the commitment key. In particular, we have to generate a commitment key for each message to be signed. So we circumvent this issue by making use of a trapdoor commitment. So what's the trapdoor commitment? The commitment key generation, in addition to the normal commitment key, it also outputs some extra trapdoor. And with this extra trapdoor, the commitment can be actually opened to any message. So now using this trapdoor property, we can actually make the simulation work. So now the honest priority simulator just sends out a random commitment in the first round. And then this commitment can be later equivocated to any message, depending on the derived joint challenge after you receive commitment share from adversary. So a bit more formal syntax. So trapdoor commitment on top of the normal algorithms for commitment, we need those algorithms. So again, you need a trapdoor commitment key generation that outputs CK and TD, and also trapdoor committing algorithm. So this outputs some commitment which looks like the real commitment. And then finally, the equivocation algorithm is needed. So now this algorithm receives trapdoor, commitment, and the pre-image. And then equivocation outputs randomness used for the commitment. Again, this randomness has to look like the actual randomness used in the normal committing algorithm. Then the security requirement is that the distribution of message, commitment key, commitment, and the randomness should be indistinguishable from the honestly generated ones. So now using this trapdoor commitment, how can we simulate? So during the first phase, simulator, instead of honestly sending a commitment to the its own share of W, it just sends out some random committed value. So at this point, the simulator doesn't know the pre-image of this commitment. And then it receives commitment share from the adversary. And then the simulator gets to know the joint challenge C. And then after this, finally, the simulator use the honest verified Zenerage simulator, then gets the W. And then finally, using this trapdoor, the simulator can open this random COM1 to W1. And then this randomness information for the commitment is again indistinguishable from the actual commitment. So this is how you can simulate a view of the adversary. And as I said before, you actually have to generate a commitment key depending on the message. So actually, in this case, for each signed query, depending on the message, the simulator has to invoke trapdoor commitment key generation, and then program the random oracle that generates the commitment key. And then continue the simulation as follows, as before. So eventually, the final secure two-round protocol looks like this. The first, each party generates the per message commitment key, and then exchange the commitments to the W, and the later open commitment to W if the rejection sampling passes. So this is how we can achieve secure two-round protocol. So some remarks about security of this protocol. So again, I already mentioned the per message commitment key prevents the careless sum attack. And the one caveat is that the trapdoor commitment actually requires computationally binding property. So security proof inevitably relies on the rewinding. So we have to use the forking lemma. So unlike the lossy identification technique, we have to rewind the adversary that leads to the larger security loss. And in our manuscript, we describe a concrete instantiation of Trapdoor commitment based on the Baum-et-al's commitment scheme by adding Michancho-Picard lattice Trapdoor. Okay, so to conclude, in this work, we constructed Fiat-Shamir-Wisz abort-based multi-party signing protocol with complete security proofs. And then our construction achieves low round complexity. And also a bit of remark about the multi-signature. So in the multi-signature, unlike N out of N signing, there's no dedicated key generation protocol. So instead, we use a standard technique. This actually follows the technique by Bellari and Nevin from 2006. So here, instead of deriving a single joint challenge, we generate a per user challenge. So by hashing the public key over each user. And then this is how we can actually construct the plain, the multi-signature that only has 2 rounds, and also that can be proven secure in the plain public key model. And there are some open questions. So of course, the extra commitment for 3-round protocol seems a bit redundant. So of course, if you can simulate the rejected transcript in Fiat-Shamir-Wisz aborts, the signature size for 3-round protocol can be improved. And also this approach makes the signature size relatively large if the number of parties is large. So how can we make the signature size less dependent on N? And also, can we avoid rewinding for 2-round protocol? This I have no idea. There might be. Okay, so that's it. Thank you very much for your attention. So yeah, I think you have some questions, so please feel free to ask.
Thank you very much, Akira. That was very interesting. Yeah, I had a question, but you answered it on the last slide regarding the key generation algorithm. So you are not assuming any secret sharing, right? There is no, as you're saying, no dedicated key generation protocol is needed.
Right. For multi-signature, yes. So basically what each party does is basically generate a local key pair. Mm-hmm. And then the adversary is able to query the oracle with a arbitrarily set up public keys. And then oracle returns a signature using that list of public key.
Mm-hmm. And I had also another question. Did you look into whether your scheme supports public key aggregation? Is it possible?
Good question. So I took a look. So I think it's possible. So so if I remember correctly, there's a public key aggregation technique from the discrete log setting. I think MPSW 19, the MUSIG. Mm-hmm. So again, the structure is similar to Schnorr. So I think it might be doable. Yeah, I think that's an interesting direction.
Okay. And then regarding the signature size, when you presented that 3-round protocol, you said the signature scales by a square root of n, right? And this one, now the 2-round protocol, how does the signature, does it change or is it still?
Yeah. So it's the same. So basically it should scale in the same way as a 3-round protocol.
Okay.
But of course, Trapdoor commitment is more expensive. So in that sense, we probably have to increase the signature size. But in this paper, this is more of the theoretical interest. So we didn't really give a concrete estimates for the signature size. It's more like an asymptotic discussion.
Mm-hmm. Okay. Okay, are there any other questions?
So in fact, I wanted to ask about the concrete security parameters, but you already mentioned it in your last comment just now, that this is more of a theoretical kind of interest. But even theoretically, can you tell me how much more expensive is a trapdoor commitment compared to a commitment?
Yes. So, I mean, so okay.
Like if you instantiate it from the same lattice-based commitment, how larger could it be? How smaller could it be? Do you have any idea?
So that particular estimation, so I haven't really given that. I think my co-host Mary has probably done some asymptotic estimates, but yeah, I'm sorry. So I think I don't have concrete number on top of my head right now, but the idea is that,
fine.
of course, you have
fine.
to instantiate so you have to, okay, so maybe I can show the, so in the Trapdoor commitment scheme, we use again, so we use random matrix A. So to support the Trapdoor, we have to generate the Trapdoor for this A using the Michanjo-Picard technique. So for this, I think some careful parameter configuration is needed, but yeah, I'm sorry, so I can't remember the number right now.
All good.
Thank you. Do we have more questions?
I've got a couple of questions. I think some of them you already answered. So for this plain key model, this is the one to prevent these rogue key attacks, right?
Yeah, exactly. Yes.
Yeah, if you kind of shift to those like per user challenges, then you can prevent these rogue key attacks. Right?
Yeah, that's correct.
Okay. And also I have kind of like a comment about the efficiency. I think you said that the efficiency, like the signature size, grows by a factor of square root of n.
Yeah.
But that's for the standard deviation. So you need to take the log of that. So the increase would be much less. Because if you have a square root of n increase, then let's say for 100 users, you would have 10 times larger signatures, but that's actually not the case. So the standard deviation increases each coefficient of standard deviation of each coefficient increases by a factor of square root of n. But when you take the log of this, the increase would be much smaller.
Oh, I see. Okay. So you're saying the bit lengths, right?
Yeah. Yeah.
Okay. Length. Yeah. Sure. Yeah. Of course. Yeah. So I was just talking about the grooves of the bound that is used for the verification.
Yeah. That's
right. Yeah. So yeah, you're right. Yes.
Yeah, I got one last question. So when you say, for example, this trapdoor commitment, so what does that exactly mean? So does that mean whoever has the trapdoor can find any message opening? Is that correct? Or
yeah, that's correct. So okay, so let's take a look. Yeah. So right. So of course, normally you should not be able to open commitment anything because that's the point of commitment. But the trapdoor. So with the knowledge of trapdoor, yes, as you said, like on any message as input, if you know the trapdoor, then you can find the corresponding randomness. And then this randomness should look like the distribution of the randomness used in the actual commitments algorithms. So that's the trapdoor commitment.
Okay. So it's not like you are decrypting a commitment, but this is like, yeah, you are essentially equivocating as the algorithm.
Right, exactly.
Yeah. Okay. Okay, yeah, thanks.
Okay, do we have more questions? I guess not. So
Okay.
I would like to thank you again. Thank you very much.